In Unit 4, we begin our study of integration. And our first lesson, Lesson 4.1, we're going to consider the problem of area under a curve. And to solve this problem, we're going to use left hand, right hand, and midpoint Riemann sums to help us find an estimate for a definite integral. And so the two standards that we're going to be addressing from the College Board are approximating a definite integral and calculating a definite integral using areas and properties of definite integrals. So there are two big ideas in calculus. The first is the tangent line problem, and we saw how that we could take a limit and actually allow a secant line to approach a tangent line as average rate of change approached instantaneous rate of change, and we were able to find the slope of a curve at a given point. The second problem in calculus is the area under a curve. And to solve this problem, Bernard Riemann, a student of Carl Friedrich Gauss, started with the idea of a rectangle. It's very easy to calculate the area of a rectangle. It's just simply length times width. So the idea that Riemann had was, suppose we take a curve that is bounded by the x-axis and two vertical lines and the graph of a function. And to estimate the area bounded under the curve on a given interval, suppose we stack rectangles that all have the same width under the function. Well, then all we have to do is determine how tall the rectangles are. Since we know how wide they are already, let's just find out how tall they are. We can use the function itself to calculate a y value for the corresponding x value of the rectangle. Then all we have to do is add up the areas of the rectangles. So this was Riemann's approach. So a couple of things that are very important. In this basic case, we're only considering a function that is above the x-axis, and so in that way we only have positive areas to deal with. And also there are basically three approaches that Riemann took. He used what were called left-hand Riemann sums, right-hand sums, and midpoint sums. So we'll take a look at each one of those. First, let's take a look at the left-hand Riemann sum. So here we have a function which is essentially a linear function, and what we have done is we have fixed width rectangles. So all of these rectangles have a width of 1 unit, and we can then determine the height of the rectangle by the intersection of the corner with the function itself. So all we have to do is take this x value, plug it into f, and we can calculate an f of x, or y value. Multiply length times width, we get the area of each rectangle. Add these up and we get an approximation for the area under the curve bounded on this interval. Now the problem is we don't get an exact answer. And in fact, in this case, we get an underestimate because you can see there's empty space between the function and the tops of the rectangles. Well, the other approach is to take a right endpoint. We call these circumscribed instead of inscribed rectangles. And in this case, it's the same approach. We have fixed width rectangles, and we find the height of the rectangles by taking the intersection of the right corner and the function. So take this x value, plug it into f, find the corresponding f of x, and that is the height of your rectangle. Do this for all of the rectangles on your interval, add them up, and we get an approximation for the area under the curve. Once again, this is an estimate, and this time an overestimate, because you can see we have all these triangular parts of the rectangles that extend above the curve. And so Riemann suggested using a midpoint approach. And this is still not perfect. It works out perfectly if it's a linear function, but if there's curvature, it's still not perfect. It may be better than the other two. So actually there are cases when all three of these may be appropriate, but you can see what's happening here. The triangle that is left blank is approximately equal to the triangle that is, or I should say the underestimate empty triangle is approximately equal in area to the overestimate triangle, and that's true for each rectangle. So in this case, the over and underestimates cancel each other out, and what we end up with is a much closer approximation, at least for this particular function.